Hello, this podcast is on describing motion with words. First, we're going to look at some background information on vector and scalar quantities. Then we're going to look at the quantities we use to describe motion: position, displacement and distance, time and elapsed time, velocity and speed, and finally, acceleration. Let's take a look at quantity, but first let me just describe this format. This is known as a Freyer diagram, and it gives us four different ways to explore the meaning of a term: the formal definition, characteristics, examples, and non-examples. So let's take a look at what a quantity is. So it's a numerical description of something that is either measured directly or calculated from direct measurements. Some of its characteristics are it's numerical, it's measured or calculated. We also know quantity as variable, and we, especially in math, use the term variable probably more than quantity, but in physics we're going to use the term quantity more than variable. Some examples: the car's speed is 44 miles per hour. Notice it's numerical. The woman's height is 6 feet 4 inches. Some non-examples: the car's speed was faster than the mopeds. This is a comparative description, not a numerical description. The woman was tall. That's a qualitative description, not a numerical description. Let's look at a scalar quantity. It's a numerical quantity that has only magnitude. Its characteristics has a numerical magnitude. It's measured or calculated, and we also will know this as a variable. Examples: we have temperature and we have weight. For instance, the temperature is either negative 30 degrees Celsius, very cold, or positive 85 degrees Celsius, very hot. But there is no direction to the temperature. The temperature may be increasing or decreasing, but it's not like it's 85 degrees Celsius in the south direction. That doesn't make any sense. Same thing with weight. This person looks like they're coming in at about 188 pounds. Again, there's no direction to that. It's not 188 pounds upward or rightward. So these things that are represented only by a number, only by a magnitude, are called scalar quantities. Now let's look at some non-examples. Here we have force and velocity. Force is not a scalar quantity. It has a magnitude, 300 newtons, but it's 300 newtons pushing to the right. And here in the example of velocity, it has a magnitude, 25 meters per second, but it also has a direction. The car is moving to the right, which we call the positive direction. Let's look at the opposite of a scalar quantity, which is a vector quantity. It's a numerical quantity again, but it now has both magnitude and direction. So its characteristics: a numerical magnitude. It has a numerical angle or a plus-minus direction on the x or y axes. It's measured or calculated, and again, we often refer to this as a variable, especially in math class. Some examples: we have velocity and force. Here, the velocity is negative 25 meters per second. The negative sign means that it's moving to the left, and the 25 is the magnitude. So I just want to make a comment here that's true in physics. When you see plus and minus signs, they have nothing to do with the value or magnitude. They have everything to do with the direction. And here's a force. So the person holding the leash is pulling up on the leash at a 40-degree angle. So this is an example where we use a plus or minus sign to show the direction, and here's a case where we use a directional angle to show the direction. Let's look at some non-examples: temperature and weight, and of course we described in the previous slide how it makes no sense for them to have direction. Let's talk about the direction of a vector. It's a quantitative description of the vector's direction, so we need to be quantitative about it. It can be a numerical angle measured counterclockwise from the positive x-axis. If we use a plus sign, that means the direction is either upward on the y-axis or rightward on the x-axis. If we use a negative sign, that means that the direction is downward on the y-axis or leftward on the x-axis. The symbol for the direction is theta. especially if we're using the numerical angle. And the units for that angle are either radians or degrees. In this class, we'll use mostly degrees. So here's an example. We have a negative sign for the car, and we have a directional angle theta of 40 degrees for the dog leash. A non-example is the directional angle of the hand's force pushing down on the lawnmower is 30 degrees. Well, this is not true. The handle here makes a 30-degree angle with the ground, but the hand is pushing down and to the left. So this force is down and to the left, which is in the third quadrant. Theta here, the directional angle for this force vector, is actually 210 degrees. So word of caution, often when you're looking at sketches or pictures, the angle they show is not necessarily the directional angle of the vector. Okay, now that we had that background information, let's move on and look at some specific quantities we use to describe motion. And position is the first one. It's the location of an object based on an origin or reference point. It is a direct measurement. It's a vector quantity. It has both magnitude and direction. Positive is upward or rightward of the origin. The symbol we use for position is lowercase x, and the SI units, the System International units, are meters, which we abbreviate with lowercase m. Some examples of position: the sprinter's positions at the starting line is x equals 0 meters. That means that they're right on the origin. Kind of makes sense in a 100-meter race that we'd make the starting line the origin, but you don't have to. The finish line could be the origin. In this example, Usain Bolt's position at the finish line is 100 meters. So again, if the starting line is the origin, then the finish line in a 100-meter race is going to be 100 meters rightward of the starting position. And let's look at some non-examples. The entire trip had a position of 20 kilometers. This describes a change in position. The 20 kilometers is a change in position, not a specific position. And the orchestra pit's location is below the stage. This is the description of a location, but it's a qualitative description, not quantitative. Moving on, let's look at displacement, and that's an object's change in position. Its final position minus its initial position. Mathematically, we would show that as delta x is equal to x sub f minus x sub I. Now let's break this down. Whenever you see delta, this triangle is the Greek letter delta, happens to be the capital delta, and it means a change in whatever variable or quantity is listed next. So this is change in position, and that's what displacement is. And the subscript here refers to the final position, and this subscript I refers to the initial position. Characteristics, this is calculated. We can't measure the change in position directly. We have to measure the final position and the initial position and then do the subtraction. That's why we call this a calculated measurement. It's a vector quantity, has both magnitude and direction. Once again, positive is moving upward or rightward. The symbol is delta x, and the SI units are meters. Some examples. Here, the boy walked from D to A. His displacement was negative 5 meters. So the boy started here at D and walked to A. This diagram is showing that the distance between D and A is 5 meters. He was walking leftward, so his displacement was negative, meaning leftward, 5 meters. Here's another example. The boy walked from A to B to C to D to A. His displacement was 0 meters. Now you may say, wait a minute, he traveled a distance. And that's true, but displacement, let's look at the definition. It's a change in an object's position. So he started here and he ended here. His position didn't change from the initial position to the final position. Let's look at a non-example. The boy's displacement from A to B to C was 8 meters. And that's not true. He walked a total of 8 meters, but his change in position from A to C was only 5.8 meters. And if you're wondering where I got that, I'm just making a right triangle here out of AB, BC, and AC. And so using the Pythagorean theorem, I came up with the change in position as 5.8 meters. Here in a second non-example, the rock displaced 5 liters of water. This is an accurate use of the term displaced, but it's a different meaning of displacement than what we mean in mechanics. Let's take a look at distance. It's the length of the path an object travels, so this is a little different than displacement. Characteristics, once again, it's a calculated measurement. It's a scalar quantity. It only has magnitude. It's also sometimes called path length. Its symbol is lowercase d, and the SI units are meters. An example, the boy walked a distance of 3 meters from point A to point B. The boy walked a distance of 16 meters from A to B, B to C, C to D, and D to A. Looking at non-examples, the boy walked a distance of -5 meters from D to A. So from D to A, he did walk 5 meters, but distance is a scalar quantity. It only has magnitude, so we do not use directional signs to show that he was actually going leftward. His displacement would be -5 meters, but his distance was 5 meters. And lastly, the cyclist traveled a distance of 120 miles. So right here we can see the distance between his house and the factory was 120 miles. We might say that's 120 miles as the crow flies, but it's a straight line. So his change in position or displacement was 120 miles, but we can see here he had to travel on an S-shaped road, and that, of course, is going to be longer than 120 miles. Let's take a look at time. It's a specific clock reading. It is a direct measurement. It's one of the few quantities, along with position, that we can measure directly. It's a scalar quantity. It has magnitude only. Its symbol is lowercase t, and the SI unit is seconds. We could say the race ended at 6:07. That's an example of time. We can say that class starts at 8 o'clock. Non-examples, class lasted 73 minutes. This is an amount of time, not a specific clock time. Or it was a long day. That's a qualitative description of time, not a numerical description. Elapsed time, the time between two events. It's the final time minus the initial time, and here again we see this delta function. Delta t means the change in time, specifically the final time minus the initial time, and it's important that you do the subtraction in that order, final minus initial. Characteristics, it's a calculated measurement. We can measure time directly, but we cannot measure elapsed time directly. It's a scalar quantity. It has magnitude only. Its symbol is delta t. SI units are seconds. Examples, the seminar lasted 6 hours because it started at 11 and ended at 5 p.m. The movie was 2.5 hours long. Non-examples, the elapsed time is 5:33 a.m. This is a specific time or clock time, not the time between two events. The 400-meter race has a longer elapsed time than the 100-meter race. Again, that's comparative, not numerical. Let's take a look at velocity. The rate at which an object's position changes, it's the displacement per unit of elapsed time. Its formula is v equals delta x divided by delta t, and we know that delta x is the displacement, final position minus the initial position, divided by the elapsed time, and that's the final time minus the initial time. So it's a calculated measurement. It is a vector quantity, magnitude and direction. Positive is moving upward or rightward. The symbol is V, and that's a V in bold type. And the SI unit is meters per second. Some examples here. The plane is flying 250 meters per second eastward, so it has both a magnitude and a direction. The cannonball's initial velocity is 20 meters per second at 30 degrees. Here, the magnitude is 20 meters per second, and the direction is 30 degrees. Notice that directional angle is measured counterclockwise from the positive x-axis. Some non-examples. The car's velocity is 58 miles per hour. Well, speedometers measure the magnitude but not the direction of velocity. So this has only magnitude, so it is not its velocity. Now let's go ahead and look at speed. It's similar to velocity. It's the distance an object travels per unit of elapsed time. So it's distance divided by time, and that looks like this. The distance, or path length, divided by the elapsed time. Characteristics, it is calculated, cannot be measured directly. Scalar quantity, it's the magnitude of velocity. So we use the symbol lowercase v, but we use it in italics to mean speed, bold type to mean velocity. Now in our class, you'll just see v. I won't use boldface and italics to distinguish the two. The SI unit is meters per second. So an example, the skydiver's terminal speed is 55 meters per second. That's about 120 miles per hour. And the car's speed is 58 miles per hour. Non-examples, the skydiver's terminal speed is negative 55 meters per second. Speed has no direction because it's a scalar, so no directional sign is needed. Lastly, let's take a look at acceleration. This is the rate at which an object's velocity changes. It's the change in velocity per unit of elapsed time. So you can see that acceleration is equal to the change in velocity divided by the change in elapsed time. Characteristics, it's a calculated measurement. It's a vector quantity. Some examples, speeding up, slowing down, changing direction. We have a tendency to use acceleration to mean speeding up, but it also includes slowing down and changing direction. The symbol is lowercase a, and the SI units are meters per second, which can also be represented as meters per second squared. Let's take a look at two examples. Car A and car B both have an acceleration of 2 meters per second. Here with car A, we can clearly see that every second the velocity is increasing in the rightward direction by 2 meters per second. In car B, this may be a little harder to see why it's a positive acceleration. Its velocity is negative, which means that the car is moving leftward. But notice by slowing down in the leftward direction, the car's velocity is actually getting more positive every second by 2 meters per second. Looking at non-examples, cars C and D have an acceleration of 2 meters per second. In reality, their acceleration is negative 2 meters per second. So if you look at example C, the car is moving rightward, but it is slowing down, which means the velocity is increasing in the leftward direction. Here in example D, the car is speeding up, its velocity is getting larger. It's getting larger by 2 meters per second every second, but it's getting larger in the leftward direction, which is why we give a negative sign to the acceleration. So the direction of acceleration can be different than the direction of motion. And when acceleration and motion are in the same direction, your object will be speeding up. When acceleration and motion are in opposite directions, the object will be slowing down. Notice, positive acceleration doesn't mean speeding up, and negative acceleration doesn't mean slowing down. If you're still a little puzzled by that, take a closer look at these two sets of charts. That wraps up our lesson on describing motion with words. Let's summarize some of the key concepts we learned. Quantities are numerical descriptions. Scalar quantities have magnitude only. Vector quantities have magnitude and direction. Direction is described using a directional angle measured counterclockwise from a positive x-axis, or plus or minus signs if the direction lies on the x or y-axis. Position, displacement, and distance are used to describe the physical location and changes in location. Velocity and speed are used to describe the rate at which an object's location changes. Acceleration is used to describe the rate at which an object's velocity changes. Let's take a look at the key math equations we learned. Displacement is the change in position, defined as the final position minus the initial position. This funny looking equal sign that has 3 horizontal lines, that means it's a mathematical description. You can go ahead and use a regular equal sign. Elapsed time, the change in time, is defined as the final time minus the initial time. Velocity is defined as displacement divided by elapsed time. Acceleration is defined as the change in velocity divided by the elapsed time. Well, this wraps up our podcast. I hope it helped, and have a good day.